Alright, this is the beginning of section 5.3. We're going to be talking about angle bisectors. An angle bisector is a ray that divides an angle into two congruent adjacent angles, okay? So if we look in this picture over here, angle QPR is going to be bisected by this ray SP, okay? Bisected means to cut something in half. So if this ray SP is cutting this angle QPR in half, that means that QPS is going to be congruent to RPS. Okay? So we have the two congruent angles. Now, our theorem, our angle bisectors theorem, says if a point is on a bisector of an angle, so here we have point S, then is equidistant from the two sides of that angle. So if this point S is located on our angle bisector, SP, then it's going to be equidistant from the two sides of that angle. So here in this picture, QS is going to be congruent to SR. Okay? It also forms a 90-degree angle. So no matter what point you pick on here, okay, it's going to be equidistant from our angle, or our angle sides, and it's going to form a 90-degree angle. Okay? The converse of our theorem is just flipping that hypothesis in the conclusion. So here, if a point is in the interior of an angle and it is equidistant from the sides of that angle, okay, so here, if this point is on the inside of our angle, okay, point D, and is equidistant from the two sides of that angle, okay, that's what it's showing us right here, then it lies on the bisector of that angle. So the converse is telling us that if these sides, these lines are equidistant that connect our point to our sides of our angle is equidistant, then this point lies on our perpendicular bisector. Our theorem says if this point lies on the perpendicular bisector, then these lines are equidistant. Okay, so make sure you know the difference between the two. Okay, so let's take a quick look at this in our geometry sketchpad file. Now, we have pointed out, I measured that DB, okay, and DC, they're equal, right? And I have this measure, BAD. Now I just got to measure out DAC. Okay, I'm going to measure that angle. And that's congruent, okay? So, because BAD and DAC are congruent angles, that means that AD is an angle bisector. If AD is an angle bisector, then this point D that lies on our angle bisector must be equidistant from both sides of our angle, which it shows, okay? DB is 3.23 and DC is 3.23. Now, if I move this, pay attention to the angles and the sides. They should stay the same the whole time, okay? No matter how big or how small this angle gets, okay, my angles that were bisected stay congruent, and the lines that connect that point on my angle bisector to the sides of my angles always stays the same. They're congruent. Okay? If AD bisects angle BAC and DB is perpendicular to AB and DC is perpendicular to AC, then BD is congruent to DC. Okay? This perpendicular part is crucial. If it's not perpendicular, then these two lines aren't going to be equidistant. Okay? Okay, now I want you to take a minute and restate the angle bisector theorem in your own words. Okay, this chapter things get a little tricky and there's a lot to remember. So try restating things in your own words. Once you have written the theorem in your own words, try to represent it on this picture, okay? Draw it in your own way so it makes sense in your head. Alright, let's look at this soccer example. This is going to go right along with our theorem of an angle, or angle bisector theorem. Okay? A soccer goalie position relative to the ball and goalpost forms a congruent angle, as shown. Will the goalie have to move farther to block a shot towards the R goalpost or the L goalpost? Okay, so if this is our angle LBR and LB, let's call this C. Oops. Let's see. C is congruent to CBR. Well, then this line BC must be an angle bisector because it bisects that angle into two congruent adjacent angles. So if these two angles are congruent, then we know that any point that lies on this angle bisector is equidistant at a 90 degree, if it's at a 90 degree angle. Okay, so he's going to have to move just as far to get from the angle bisector to L, as well as from the angle bisector to the side R of the goalpost, because this angle is bisected, right? So if we draw a line that is perpendicular to the side of our angle, it's going to be equidistant to this line that we drew from our angle bisector to the side of our angle, and it's perpendicular. Okay, so just to summarize, the solution is the congruent angle tells you that the goalie is on the bisector of angle LBR. By the angle bisector theorem, the goalie is equidistant from BR and BL. Okay, so the goalie must move the same distance to block either shot. Now let's look at this example. Find the measure of angle GFI. This is going to be using our angle bisector converse theorem. So we're trying to find the measure of this piece right here. But we can't just necessarily assume that it's 42 degrees just because you think this might be an angle bisector. We got to figure out if this is or not. So because JG is perpendicular to FG, right? And JH is perpendicular to FH, and these two are equidistant, or they're congruent, so JG is congruent to JH, they both equal 7, we can then say that FG, or FJ, is an angle bisector. So this point J is on our angle bisector. These lines are equidistant at a perpendicular, okay? Therefore, this is an angle bisector. So if it's an angle bisector, I know that these two angles are congruent. Therefore, the measure of GFI is going to equal 42 degrees. Okay. This next example. For what value of x does P line lie on the bisector of angle A? Okay, so we got to figure out if this point lies on the angle bisector that isn't constructed yet. So, from the converse of the angle bisector theorem, you know that P lies on the bisector of angle A if P is equidistant from the sides of angle A. So therefore, BP must be equal to CP. Okay, so we're going to set those two equal to each other. When we do that, okay, BP is x plus 3, CP is 2x minus 1. You're going to solve for x. You're going to get x equals 4. Okay, so if you plug that back in, you're going to get BP is 7, okay, and 2 times 4 is 8, minus 1 is 7. So BP is congruent to PC. Therefore, the point P lies on the bisector of A when x equals 4, okay, only at x equals 4. So then we can go ahead and say, okay, I know that point P must lie on this angle bisector. This is an angle bisector, then these two angles are congruent because these lines are equidistant. They're the same. Okay, we're going to try these next ones together. So if this angle is 27 degrees and this angle is 27 degrees, this line must be an angle bisector. So to solve for x, I'm just going to set x equal to 15. Well, x then equals 15. Okay? For 2, now we're looking at the converse, all right? We're trying to figure out if these angles are congruent. If this point on my angle bisector is equidistant from the two sides of my angles, then this line right here must be an angle bisector. Therefore, these angles are congruent. So I'll say that again. The converse says that if this point is equidistant, right, these two are congruent, these two lines are congruent from the sides of my angle, then this line, right, this ray right here is an angle bisector. If it's an angle bisector, it bisects this angle. Therefore, these two angles on the inside are congruent. So I can set 3x plus 5 equal to 4x minus 6. Subtract 3x from both sides. I get x minus 6 equals 5. Add 6 to both sides. X equals 11. Okay? Try this one on your own. Okay, when you solve it, you should have set 5x equal to 6x minus 5 to get x equals 5. Okay, you should have seen that these angles are congruent, therefore this is an angle bisector, and therefore these are equidistant, they're congruent. You can set them equal to each other. Here, do you have enough information to conclude that QS bisects PQR? Take a second, pause the video, and think what you can get. Okay, you should have said no, and the reason why is because we know nothing about these angles being congruent. We know that these lines are congruent, but they're not perpendicular to the sides of our angles, so we don't know that this is an angle bisector. Okay, so this should have been no, because we don't know that SP is perpendicular to PO or PQ, or SR is perpendicular to QR. So we can't say, we don't have enough information to assume that QS is a perpendicular or is an angle bisector. Alright, now we're going to use Geometry Sketchpad to look at this point H. Okay, this point H is where my angle bisectors all meet. Okay, so this is all the green lines are my angle bisectors. So you should be writing that in your notes. Okay, these orange lines, okay, are the lines that connect, like we talked about, are the point on our angle bisector to the side of the angle. So here we have angle ILK. LH is the angle bisector. H is a point on that angle bisector. And HK is perpendicular to LG. HI is perpendicular to LI. And these two, okay, HI and HK, are equidistant. They're the same. So here we have an angle bisector. Same goes for the rest of these two. Okay, an angle bisector starts at the vertex, okay, and it bisects this angle. Now, if I were to manipulate this, notice how these three lines that connect our point to the side, or our point of congruency to the side of our triangle, all stay the same no matter how I move this triangle. Okay, doesn't matter. What changes, okay, is the length of our angle bisectors. That doesn't do anything, though, to these three lines. So what I'm trying to get at on the next page of your notes, okay, you'll be able to see this. I'm not going to go to it because we're running out a little bit of time. This is talking about Theorem 5.7, so you should be looking at this on your own. Now this point H is called the incenter. It's a point of congruency where the three angle bisectors of the triangle intersect. Okay, so this is called the incenter. The incenter is equidistant from the three sides of the triangle, which we talked about, okay, these orange lines. And as you notice in the sketchpad manipulation, the center is always located inside of the triangle. Okay, this circle just represents that these lines connecting to the incenter are equidistant. They're the same. So it's the radius of this circle.